So in this lecture, we prove the first isomorphism theorem for groups. So let's recall, we have a group G, and H is a normal subgroup of G if every left coset equals the corresponding right coset for all X in G. And there's an equivalent condition, which is that XH X inverse is contained in H for all X in G. And if H is a normal subgroup, then the set of left cosets G mod H is also a group with the multiplication defined by XH times YH, the product of those two cosets, is the coset XYH. And the function pi from the group into the quotient group is defined by pi of X equals the left coset XH is a homomorphism. It's called the canonical homomorphism. So it's a sort of a fundamental homomorphism, and that's what it is. We also have one other observation. This was a theorem, or maybe a lemma, but if F from G to G prime is a homomorphism, from every homomorphism we can get a normal subgroup. Then the kernel of F, which is all the elements in G, such that F of X is the identity in G prime, is a normal subgroup of G. So one way to get normal subgroups is as kernels of homomorphisms. And what is often called the first isomorphism theorem for groups says the following, that F from G to G prime be a homomorphism with kernel K, let H be a normal subgroup of K, H could be K itself, then there exists a unique homomorphism F tilde from G mod H into G prime such that the following is true. Let me draw a picture and then it's clear what the statement means. Here is G. We have a homomorphism to G prime. We have a normal subgroup H contained in the kernel. So there's a canonical homomorphism pi from G to G mod H. And the theorem says then that there exists a homomorphism F tilde from G mod H to G prime, such that if you go from G to G prime, either along this path or along this path, you always end up at the same place. What that means is that F tilde composed with pi, go first pi and then f tilde is equal to f. And if, in fact, H is the whole kernel, then this function f tilde from G to G prime is 1 to 1. And so G mod H, G mod K is isomorphic to the image of G under F. I'll explain that again in a bit more when I get to it. So this is the main statement. This is really kind of a corollary. So how does the proof go? So suppose there exists a homomorphism f tilde from G mod H to G prime. Then what can we say? So then f tilde of a coset xh, well, that's f tilde of pi of x. Pi of x is xh. But f tilde pi is the same as f. So we have no choice about what f tilde can be. So f tilde, if it exists, is unique. This says there's really at most one function from here to here that's a group homomorphism and satisfies this condition. But how do we prove existence of f tilde? Well, we have to define a function on cosets of h. So if xh is equal to yh, what does that mean? That means that x inverse y is in h, and h is contained in k, which means that which is the kernel. Which means that f inverse of xy, means the identity is f of x inverse y, which is f of x inverse f of y, which means f of x equals f of y. So if you have two cosets, if you have one coset represented by x or by y, f of x equals f of y, and we define f tilde of xh to be f of x. So this fact says that this function f tilde is well defined, and f tilde of a product of two cosets, that's f tilde of the coset xyh, that's f of xy. F's a homomorphism, so that's f of x, f of y, which means this is f tilde of xh, f tilde of yh. So f tilde is a homomorphism, that's what we needed, and pi f tilde is f. So this proves the existence of a unique function f tilde. Suppose in this picture, h is actually equal to k. So recall, f tilde of xh is f of x. So f tilde of xh, which is f of x, this is equal to the identity in G prime if and only if x is in the kernel. Which means xh is H, is the identity. G mod H or G mod K. So therefore, F is 1-to-1. Now, let's note the following thing. Suppose we have a homomorphism F from G to G prime. So the kernel of F, this is all X and G prime, such that F of X is the identity. So this is a normal subgroup of G. What is called the image of F, or F of capital G, is everything of the form F of X, X and G. Because if X is in G, F of X is in G prime. This is a subset of G prime. This is a subgroup of G prime, not a normal subgroup necessarily, but a subgroup. What is the proof of this fact? Well, if Y1 and Y2 are in F of G, then there exist X1 and X2 in G such that F of X1 equals Y1 and F of X2 equals Y2. So Y1, Y2, which is F of X1 times F of X2, but that's F of the single element X1, X2. So that means this is in F of G. So F of G is closed under multiplication. Well, F of E is the identity in G prime. So E is in the image of F. And third, if Y equals F of X is in the image of G, then Y inverse, which is F of X inverse, but F of X inverse is F of the element X inverse, is in the F of G. So therefore, F of G is a subgroup of G prime. So if we have a function F from G to G prime, this is really, you can also think of this as a function from G into its image contained in G prime. And if K is the kernel, we have a function F tilde from G mod K into F of G. So this function, this F has kernel of F is K. So for every Y in F of G, Y is equal to F of X for some X in G, and F tilde of the coset XH is F of X, which is Y. So F tilde is onto F of G. And we already saw that F tilde is 1-to-1, which means F tilde is an isomorphism. So G mod K is isomorphic to F of G. That is the first isomorphism theorem. It's not the only isomorphism theorem. And it's worth perhaps proving what is also called the second isomorphism theorem. So for that, we need to recall what is a product set. So if you have sets X and Y in a group, the product set is the set of all products, X times Y, where X is in X, Y is in Y. And we're interested in the case where we take two subgroups. So if H and H prime are subgroups of G, then the product set H times H prime is not necessarily a subgroup of G. But there's one important special case when it is, and that is the following. So this is a lemma in the notes. So we have G a group, N a normal subgroup of G, and H any subgroup. Then the product set NH, which is everything of the form X times Y, where X is in N and Y is in H, is a subgroup of G. So the product of two subgroups is not necessarily a subgroup, but the product of a normal subgroup times a subgroup is always a subgroup. Proof. So suppose we have X1, X2 in N, and maybe just to emphasize the fact that to distinguish elements of N from elements of H, well, everything is from X times H, where X is in N and H is in H. And H1, H2 are in H. So I want to show the product set is closed under multiplication. So I take X1, H1 and X2, H2, and I multiply them. So I want to show that can be written as something in N times something in H. So I can write this like this: X1, H1, X2, H2, and in here I'm going to put in, X1, H1, X2, H2. And in here I'm just going to put the identity in the form H1 inverse H1. So if I factor this, this is X1 times H1, X2, H1 inverse times H1, H2. Now, N normal implies H1, X2, H1 inverse is equal to some element X3 in N. Then as normal, if you conjugate any element in N, you stay within the subgroup N. So this is equal to X1, X3 times H1, H2, and this is definitely an N times H. So NH is closed under multiplication. E is E times E is in NH. So the identity is in NH. What about inverses? So suppose I take an element in N, an element in H, and I look at XH inverse. I have to show that's in NH. So XH inverse is H inverse X inverse, which I can write as H inverse X inverse H, H inverse. And this is in N because X inverse is in N, and it's a group, subgroup. And this is conjugation by H inverse. So this is in NH. So we're done. So NH is always a subgroup. And what is the second isomorphism theorem? Says the following. Suppose we have a group and it has subgroups N and H. So N, normal subgroup, H, an arbitrary subgroup. So if I have two subgroups, the intersection is a subgroup and it's contained in both of them. And if N is normal, NH is a subgroup and it contains N and it contains H. So N is a normal subgroup of NH, and intersect H is a normal subgroup of H. If N is a normal subgroup of NH, we have a quotient group NH mod N. If N intersect H is a normal subgroup of H, we have the quotient group H mod N intersect H. And the theorem says these two quotient groups are isomorphic. So I think I'll prove that in the next lecture, but let me just make sure I prove the one thing which I don't think I proved explicitly so far, which is the intersection of two subgroups is a subgroup. So this says in general, let H1, H2 be any family of subgroups of G. Then if I take the intersection of all these subgroups, however many there are, this is a subgroup. And the proof is as follows. Now maybe I'll just do it for two subgroups. And the generalization to an arbitrary finite or infinite family is exactly the same. H1 intersect H2. So suppose Z1 and Z2, or suppose X and Y are in the intersection. That means X is in H1, Y is in H1, so XY is in H1. And it also means that X is in H2, Y is in H2. And again, because H2 is a subgroup, XY is in H2. So XY is in both of them. So XY is in H1 intersect H2. So this intersection is closed under multiplication. Second, of course, if H1 and H2 are subgroups, each of them contains the identity. So the identity is in H1 intersect H2. And finally, if X is in H1 intersect H2, then X is in H1. So X inverse is in H1. X is also in H2. So X inverse is in H2. So X inverse is in H1 intersect H2. So the intersection of two subgroups is closed under multiplication, contains the identity, and contains the inverse of each of its elements. So that's why it makes sense here when I have two subgroups N and H to claim that their intersection is a subgroup. And the rest of that theorem I'll prove in the next lecture.